Hello everyone, welcome and thank you for being here. I'm Alex McDaniel, the project manager for K-JAMM Engineering, and we are here to talk about the Acton Lake Dam project. Before we get into the project, I'd like to introduce our team. Like I said, I'm Alex McDaniel, the project engineer and the water resources engineer. We have Jonathan Syed, our structural engineer, Kevin Goldner, our environmental engineer, Carlos Bribiesca and Maya Heidke, our geotechnical engineers, and Matthew Fitzpatrick, our transportation engineer. Thank you guys. So a brief introduction to our project. Acton Lake is in Butler County, Ohio, just northeast of Cincinnati in Oxford. The Ohio DNR has asked us to make changes or replace the spillway structure, the weir structure, the retaining wall, and to address concerns with seepage and stability concerns of the earth dam of the project. Let's just go ahead and jump into the hydrology side of things. My scope was to remove and replace the existing drainage structure and to design a water elevation control system. Here are some of the values that I used in my design calculations, the most important one being the peak flow discharge. That was used for most of my calculations. In order to address the water elevation control system, we went ahead and designed a sluice gate design, which is found on the north wall of the dam. In order to do this, we had to find the capacity of the spillway under the weir. Then we used Bernoulli's equation to find the flow exiting the gates. And from this information, we were then able to determine the size and the amount of gates needed for our design. Our final design called out to be 7 gates, dimensioned at 2 meters by 2 meters. The spacing of the gates is 10 feet from the edge of the wall, 11 feet between the gates, and 12 feet from the ground elevation to the bottom of the gate. The gate is operated by a mechanical actuator, so that no hand adjustments are going to be needed for the project, that it can all be done remotely. And we got our gates from a company in Ohio called Waterman Industries. They give us a pricing about $50,000 per gate. Since we need about 7 of them, that will bring us around $350,000 for the gate portion of our design. So I'd like to hand it off to John to talk about the structural part of our design.
All right. Thank you, Alex. Hello, everybody. My name is Jonathan Syed. I'm responsible for the structural portion of this project. When this project began, I was tasked with analyzing the current structure and through that analysis, design the future structure to be used. Now, the first design item that I was responsible for was the OG weir. Now, this will act in accordance with Mr. McDaniel's sluice gates. Now, this will be used only in extreme flood events. When the water cannot be passed through the sluice gates, it will pass over the weir and be safely discharged into the spillway. The weir itself has a 60-foot thickness extending towards the spillway. It is about 46 feet in height and 200 feet long. Now this shorter portion underneath is called a cutoff wall, and that is used for preventing seepage underneath the dam. And this is just because we have a clay layer underneath and it is prone to sinking down and having water travel underneath. And by implementing this, we are hoping to eliminate that. The next design item was the retaining wall. Now this ties into the southern portion of the OG weir. And the primary reason for using this is to retain the soil while also tying in the OG weir to the earth and providing it the stability of the earth to keep it stable. Now the retaining wall, there will be 8 separate sections, and they are all designed similarly to the one you see here, just with a variation in height from about 12 feet to a height of about 32 feet. And as you can see here, these are the sections. It starts down here with a 12-foot section and reaches the max height of 32, and then the sections beyond that go to about 24. Finally, I was responsible for designing a cofferdam. The purpose of a cofferdam is to retain the water, provide a temporary enclosure while we are constructing the dam. These will be constructed in phases. The first phase will be designed for the retaining wall and the OG weir. And when that section is complete, we will remove that and we will create the second section for the sluice gates to be constructed. Now these cofferdams are made up of driven H-piles, which are size W14 by 120, cross bracing, which is W8 by 36, and then steel sheeting, which will make up the wall of the cofferdam, and these will be PZ27. And this is just a front and back view of the cofferdams that will be used. As you can see, this is the cross bracing between the driven piles and the PZ sheet piling behind it for the retaining. Now I would like to hand it off to Kevin Goldner, who will talk about the environmental portion.
Thank you, Jonathan. People in the back can hear me okay? Good on volume? All right. As Jonathan said, I am the environmental engineer on this project, and our scope consists of 3 separate items. The first of these being water quality. We need to ensure that all water being discharged downstream has an oxygen saturation of 90%. In addition to this, we must prevent supersaturation of other gases such as nitrogen, which would cause our fish to get sick, and we don't want that. In addition to this, our second portion of the scope is we need to allow the passage of fish between the lake and the creek that is downstream from the side of the spillway. This obviously allows the migration of fish, allows them to repopulate the lake, and it's a very natural way to allow them to keep their migration patterns. And the third portion of this scope is erosion control. We don't want to erode any sediments as we're discharging our water downstream. Erosion of sediment would be bad, and we will be preventing that. Now, the way I've decided to address the oxygen content issue is a stepped spillway. Now, the way that this works is water flows over these steps and it turbulently mixes with the air. This causes the oxygen level in the water to increase. The existing water conditions are that it's at 15 degrees Celsius with 3.0 milligrams per liter of oxygen content, which is 30% saturation at 15 degrees. We need to achieve 9.09 milligrams per liter. That's our 90% cutoff rate. Based on these 2 values, I was able to determine the size and the number of steps that we would need in order to achieve this value. These are the dimensions of the steps. After all of my iterative calculations, we will in fact be achieving this 90% saturation. Moving on to the fish passage, I've designed a nature-like fish passage. It basically just looks like a stream with stone weirs. The way that these stone weirs work, they create resting pools for the fish. It's basically a stone wall with an opening in it. The opening obviously allows the fish to swim through, while the wall blocks off the flow rate so the fish are able to rest in between our pools. The opening in the weir is what allows the fish to navigate through the passage, helps it know which direction to swim upstream. The design species used in this design is the gizzard shad. It's the main forage species in Acton Lake, so it's a pretty slow swimming fish, and we need to accommodate the weaker fish being able to swim upstream. The opening in the weir, however, was designed for the largemouth bass so that the large fish can fit through the opening while the small weak fish can still swim through the opening. The gizzard shad, like I said, controlled the flow rate at 4 feet per second. In order to control the flow rate coming into the fish passage itself, I needed to design a form of flood control structure. I decided on a 4-sided box culvert that is 5 by 5 feet and 100 feet long. This connects the fish passage to the lake itself, and it's on the north end of the fish passage. And to give you an image of how things work together here, so here are our sluice gates. They flow into this channel, down the stepped spillway, into this channel, and this is our erosion control right here. It's a layer of geotextiles, which is a fabric that you place on top of the soil, and then you place the riprap, which is basically just large stones that breaks up the flow of water and slows it down. You place that on top of the geotextiles, and it prevents the erosion of soil into the 4 Mile Creek that's downstream. Up here, we have our box culvert that's at the inlet of the lake, tying into the fish passage, which will run along the east end of the dam and spillway. And down on the southern end, it will reunite down in 4 Mile Creek after the portion of riprap. I would like to pass it off to my Heidke and Carlos in order to talk about the geotechnical.
Thank you, Kevin. Like he said, I'm Maya Heike, and this is Carlos, and we were tasked with the geotechnical aspect of the project. So 2 things that we were working to design for were any high water pressures that would cause seepage through the dam, and any stability concerns at the toe of the dam which would cause overturning. And through GeoStudio 2012, we could input how the dam was, the features of it, and get an analysis, and then we were able to create a design. So we were given boring logs of the dam, and from those boring logs, we chose section BB because it fell right in the middle of the dam, and we based a lot of our analysis off this section. As you can see here, it is a cross-section of Station 9, which is BB, and it just shows the different layers of soil that are underneath the dam, and these soils were important to us because then we were able to combine them into the analysis that we did. So this is a description of the soils, just more in depth. Clay layer, that was through a lot of the dam. We had an embankment core, that's like the center part of the dam, and that was also clay, as well as the shell was also a clay material. We had clay gravels underneath the dam, as well as various sands throughout the dam.
Okay, so we use a program called GeoStudio to analyze seepage and stability in the dam. So like Maya said, we were able to put in the most common type of soils. So they're all color-coded there. The blue is like a foundation and a gravel type of soil. And the green is an embankment shell. And the yellow is an embankment core. So this is the finalized stability analysis. Basically, what the surface underneath that wedge is called the critical slip surface. So it is the most probable failure plane. So if it would fail, that would be the plane that it would fail in. However, the green shade indicates a 1.8 factor of safety. So you could think of factor of safety kind of like a reliability. Since it is higher than the required 1.5 factor of safety, we could assume that the dam is stable. So moving on, this is our seepage analysis. So the existing conditions, as you can see, the path, the blue line kind of shows a path of water going through. Seepage could cause a state called piping, which could really affect the stability of the dam, and could cause erosion within the dam. So our solution was to put in a trench 10 feet deep by 5 foot wide. And basically what this would do is it would alleviate the pressures from that water seepage line. And what it would do is it would go into the rock fill, and it would go into the our trench that we're building, and it would lead the water into the back into the spillway.
So here is just a diagram of our trench. It goes along the dam, and as he said, it is 5 feet wide by 10 feet deep. The white lines that you can see that are already in the picture were granular fill, and we just left them there because they will also help transporting any water into the trench. And then on the east side, it exits into the spillway. And here is a cross section. You can see it is 1,040 approximately feet long, and so this granular material is a sandy material. And then at the last 10 feet, we have a slotted pipe.
Okay, so this is the last portion of our trench. Basically, the last 50 feet has a slotted drain pipe that is 1 foot in diameter, and it has slots on the top to help collect the water from the top and collects water from the side, and basically it just helps to transport the water into the spillway. And I will pass it on to Alex to talk about transportation. Matt.
Good afternoon, everybody. My name is Matt, not Alex, and I'm the head transportation engineer for K-JAMM Engineering. The primary scope that I had to deal with this past year actually, was to increase the accessibility to the lake, as well as the capacity for those wishing to use the lake. And I did this by designing a roadway and a parking lot, as you can see there. Now, all of my designs were based off of a certain design vehicle, and in our case, we used one called as P/B, which is a car with a boat trailer, to be a total length of 42 feet and a turning radius of 24 feet. Now, all of my designs, after using that design vehicle, came out to be this list right here with horizontal and vertical curves for the road, the pavement thickness for both the parking lot as well as the roads, intersections design at the northern intersection right here, as well as at the existing roundabout right there. There was a signage and striping report for both the parking lot as well as the intersections and roadway, just the type of painting and signs that would be installed during construction, as well as the boat ramp right here at the northern part of the parking lot. Now, the first and primary portions of my design came with the curves, first of which was the horizontal curve, as you can see to be just under 1,000 feet. There'll be a close-up picture after this, extending at 917 feet. The vertical curve, which thankfully only had an elevation change of 15 feet, so it made for a very simple design. You know, when you have to have a very large elevation change, it makes designs more difficult, and in our case, there was only 15 feet along the length of the horizontal curve. There were also two straight portions of the roadway, which are just as they sound, straight portions. There were no curves to them, so the designs for those were very simple as well. And each of the points, what we call stationing on roadways, when you have certain, I guess, design points where you have calculations, and these calculations to help with constructability were chord lengths, elevation lengths, or calculations, and deflection angles. This just helped the construction managers and construction teams to be able to construct the portions of this roadway very simply and without problem. Here's a close-up of the parking lot, a 3D rendering. As you can see, there will be 4 light posts at each end of the normal-sized parking spots. On this side, you can see the extended parking spaces for our design vehicle, which are over 50 feet, so well enough to account for the 42-foot-long design vehicle and for bad driving and whatever other factors may come into play there. And right here at the northern portion, like I said earlier, you can see a boat ramp, and that will be widely accessible for those wishing to access the lake, as there are no boat ramps below the middle of the lake. There are boat ramps for the community on the top portion, but not below. Here's a close-up of the roadway. You can see the lengths a little bit better, with our horizontal curve being a total of 919 feet. You can see the placement of the parking lot, which played a large part in the positioning of both the straight portions of the road and the horizontal curve. And here's the vertical curve. Basically, what you need to take away from this is that there is, like I said, a total of 15 feet of elevation change from the beginning of the horizontal curve to the end of it. As for the pavement design was consistent throughout the parking lot as well as the roadway, with a top asphalt layer of 3.5 inches. And the base layer, when I originally did the calculations, was only needed to be 1 inch, but that, when constructing, is difficult and rather unnecessary to deal with. So after I did the calculation, after I used a minimum AASHTO, which is our guidelines, base layer of 4 inches, the subbase was then determined to be unnecessary, making constructability significantly greater and easier. As for the first intersection that I designed, that was at the northern portion of the roadway. You can see here it consists of 2 simple curves that will be installed, one being 30 feet. That's just a simple radius of 30 feet with no offset or taper, simply because there will be a stop sign installed there, so you couldn't move the roadway out anymore. On the other hand, though, there is a 20-foot simple radius with an offset of 2.5 feet and a taper of 10 to 1 feet. This just pushes that curve a little bit away from the intersection, allowing people to make that turn more smoothly, especially with the boat trailer hitch. It's going to be more difficult to make a very hasty curve, so this just makes it much more smooth and safe for those wishing to use the roadway. And because of these 2 radiuses and turns, there's going to have to be Significant tree clearance, as you can imagine, when turning right onto a roadway, you need to be able to see far enough to your left to see if there's any oncoming vehicles. As for the roundabout, this roundabout was pre-existing, it was already there. There is a maintenance road off to the east side of the roundabout that maintenance crews can use to access the dam. We're not going to be touching this, and because of that road, we're also not going to be installing a curb. All we will be doing is installing the northern portion, the northern leg of this roundabout. As you can see, it'll have a simple 72.5-foot radius on that curve, as well as an apron of 27 feet. Here is the boat ramp configuration. So Alex McDaniel, our head engineer and hydrology engineer, had to design for fluctuations in the water elevation during a storm or during a drought, and we wanted the boat ramp to be able to account for those so people could still use the lake when there hadn't been rain for a while, or even if there recently had been a really large storm. And that's why there is a total of 15 feet above water level of ramp, as well as 10 feet below, to allow for plenty enough fluctuations in water level where people could still use the lake. And now I'd like to pass it back off to our project manager to go over the budget.
Thank you, Matt. So here's our overall budget for the project. As you can see, the structural and water resources makes up the most of the project due to the amount of structural concrete and steel needed for the structures. That comes out to be about $7.3 million. The environmental came out to be $500,000. Geotechnical, $64,000, and the transportation a little over $1 million, totaling about $8.8 million with a 5% contingency to put us at a grand total of $9.3 million for our project. Now I'd like to invite my group back up and open the floor up for any questions.